Hi, so I want to talk about three-sat algorithms and how to make them as fast as possible. So the three-sat problem, if you don't know, is we want to satisfy a Boolean formula. So each one of these x, y's, and z's right here is some literal, meaning that it's just some Boolean value. So like x, if I set x to be true, that I'm allowed to do that. I can set x to be false if I want to. We have ors in between the literals right here. Literal just means either the variable appears in its positive form, like this x here, or the negated form, which is this a negation of y right here. So this or is Boolean or. So let's just say that I set x to be true and y to be true and z to be false. I'm allowed to do that. Then x is going to make this, what is called a clause, true. So this part right here is what is called a clause. And what we want to do is to set the values, the variables of this whole formula here to be either true or false, such that if we evaluate the whole formula, the result is true. So if I set, let's say, x to be true, then it doesn't matter what y is set to, doesn't matter what z is set to. This clause is true. Okay. There may be some problems over here where this phi over here can be a whole set of clauses because of ands in between. So this three-set formulation is a clause Boolean anded with a whole bunch of clauses over here. Okay, so one clause and a whole bunch of other clauses. So clauses are three variables or fewer, although we can say exactly three, where they are all ORed together. And what we want to figure out is there a combination of trues and falses that I can do to these variables such that when I evaluate the whole formula, the result is true. Okay, so what I want to do here is, even though this problem is NP complete, I want to look at fast algorithms, quote unquote fast algorithms, and see how fast we can actually get this, even though we don't know of a polynomial time algorithm for this problem. So let's get started. All right, so let's talk about just a naive brute force algorithm, and then we'll try to iteratively improve upon that. So let's just say that we have some input instance, let's call it C, which has, let's say, n variables. And let's say has m clauses. Or we can switch it. It doesn't actually matter what is the n and what's the m here. So let's say n variables and m clauses. Well, the total number of possible truth assignments to the n variables here is 2 to the n, right? So I have 2 to the n possible ways of assigning all of the variables. And what cost is it to evaluate the formula? Well, if I set, let's say, x to be true and y to be false and z to be true or something, then I only need to go through the formula one time to figure out the truth value of the whole formula. I may have to go through the whole formula to actually figure out whether it evaluates to true or not, but it's only linear in the size of the formula. And since each of the clauses has 3 elements in it, at most, we can even assume exactly 3, then that means that we are taking order 2 to the n times m time. So the runtime here for a brute force algorithm, which is just try all possibilities, will take big O because of the constants in like looking up the variable truth assignment and setting it in the formula and the actual length of the formula, but it's going to be some constant times 2 to the n because that's the number of truth assignments. So that comes from the number of truth assignments. And then multiplied by the size of the formula, which is m in this case. And since we know m is going to be at most 3n, in fact, you can even assume it's exactly 3n, this is going to be big O of 2 to the n times n time. And we usually will we will shorten this to sometimes saying big O star of 2 to the n, because that little n on the bottom is kind of irrelevant because the 2 to the n is so much bigger than the n. Technically, in terms of big O, I should include it, but in terms of like getting an algorithm to be faster, the 2 to the n is going to dominate way more than the n actually is. So this O star is kind of like big O, but we throw away any polynomial factors that are multiplied by the bigger guy here. Focus on the main picture, which is the exponential part, not the polynomial bit. So is this the best that we can do? It turns out, no, we can do significantly better than that. And let's get started on those. All right, let's try to actually get a faster algorithm than just the brute force idea. And I wrote this right here for a reason. So let's focus on that. So what I'm going to do is I'm going to copy this down so that we can play with it. All right, so we got a little clause right here and a formula, okay? So the thing is that if this is satisfiable, then one of these guys is going to be set to true, obviously, or at least evaluate to true. And if y is false, then this evaluates to true. So either x is true, y is false in this case, or z is going to be true. I'm gonna write it this way so that we don't have to worry about the negations, because it won't actually make a difference. We're thinking about these either in the positive or the negated form. It doesn't actually matter here for this purpose. So let's actually think about this. Well, it's either the case that if this whole thing is satisfiable, that either x is true or it's false. One of those two is the case, or both. They might have a satisfying assignment with x being true and another one being where it's false. But if it is satisfiable, one of those two is the case. So let's say that I'm going to call this a big modified formula phi prime. So phi is the rest of the formula, which for the moment I'm not caring about. Phi prime is the big guy, is the big formula. And let's say that we're trying to solve 3-sat, and I'm going to write it as a function. So let's say I want to call 3-sat of, actually I'm going to use a different color for this. So let's say that I'm going to write pseudocode here. So 3-sat of phi prime. Okay. So then what are we going to do? Well, so this is going to be a recursive algorithm, so we need the base case. So what is a base case here for phi prime? Well, phi prime has no clauses in it whatsoever. It's satisfiable automatically. So then let's just have that right here. So if phi prime is empty, then it automatically trivially is satisfiable. So return true. Okay, so it's automatically satisfiable. Otherwise, it must have at least one clause and must look like something like this. So it must be some clause anded with something else. Maybe this is empty too. And maybe we could have a base case for that, but it turns out it's not necessary. So what we can say is that this formula right here, this phi prime, is something of the form x or y or z and something else. And I'm just going to set that to be what phi prime is. So phi prime is some clause I'm going to call x, y, z, and some other stuff, some other clauses I'm going to call phi. So then let's just try the two possibilities then. So then what I'm going to do, if we recursively call 3-sat on this modified formula right here, where I'm going to use some notation here where I'm going to set x to be true in this formula, okay? So this is the whole formula. This is the big guy. And this notation is saying throughout the whole formula, set x to be true. So if this thing is true, then that means there is a satisfying assignment where x is true and then some other stuff, false and true depends, then we can return true here. So let's return true. Then in the other case, let's test the same idea, but where we set x to be false. So if 3 of phi prime, x to be false, then if the 3 comes back and says, yes, it is satisfiable, then there is a satisfying assignment where x is false. And so therefore, I'm going to return true here. But if it's neither the case that neither of these is satisfied, then there's no possibility of there ever being a satisfying assignment. Because we tried the true case and we tried the false case, neither of them return true. So we can just return false. Okay, so return false. And for the eagle-eyed among you out there, this is not better than the naive solution that we had, sadly, because we're only eliminating one variable at a time, essentially. Eliminating just means it hasn't been fixed to a value yet. So let's say that there are n variables right here. This modified formula in here that I'm recursively calling with has one fewer variable, and so I have 2 recursive calls of size n minus 1, and you can figure out pretty easily then that we're going to get 2 to the n runtime. So t of n, the time to work with n variables, is 2 times t of n minus 1 plus big O of 1. There's only a order 1 amount of work at each point here. And if you evaluate this is also 2 to the n times something. It'll be n in this case, which is really annoying. So let's think about this a little bit. So it turns out that we can do a little bit better in handling these 2 cases. So I'm going to move these down a little bit. Let's see if I can get it all in one go. Yes, I can. All right, so let's think about this. So let's say that we have to do this because, or at least at this point we have to do this. So suppose that this returns false, that setting x to be true is not satisfiable. Then that means that if there is a satisfying assignment at this point, right here, then if there is one, x must be false, okay? Because there's no other possible value. So there's no point in doing this right here, because if it is satisfiable, we already know that x has to be false at that point. So instead of focusing on x, which has to be false, let's move on to another value and work with that one. And that's what we're going to do. So I'm going to bring this pink line back up. Oh, I lost a few along the way. So let's see. So I'm going to have x to be false right here. But what I'm going to do next is I'm going to look at the case where y is set to true. So I know x has to be false no matter what. So we might as well set another variable and then work with that. So here I'm going to set y to be true. So this is saying in the whole formula, fix x to be false everywhere, fix y to be true everywhere. Okay? Well, if this is not satisfiable, then that means that x has to be false and y also has to be false in order for this to be satisfiable at all. So what we can do now is to return what we can return immediately here, calling 3set on the whole formula where I set x to be false, y to also be false. So if that is satisfiable, we might as well just set the third one to be true. So I'm going to set z to be true. And I'm just going to return that guy. Okay? And that's it. It turns out that, well, let's try to analyze the runtime. So the runtime is, well, t of n. I don't know what that is yet. Well, we're going to make a t of n minus 1 call right here because we're fixing one variable. So t of n minus 1. And there's only one of the n minus 1s here. This one has two variables fixed to get there, and we're making a recursive call. So that's 1t of n minus 2 because I fixed two variables. And then this one has three variables that are fixed. So, and there's only one of those, so I'm going to add a single t of n minus 3. And the time to combine all of these is going to be some polynomial. So some plus n to the c or something. Okay, well, where c is just some constant or linear. It doesn't actually matter because it's just going to be swallowed up by the rest of the runtime anyway. Okay, so then if we actually try to evaluate this, then it turns out that this is better than 2 to the n runtime. And the techniques to actually solve this are way beyond the scope of this video. It uses something called the Acrobazi method or the characteristic polynomial. And I will eventually, hopefully, do a video on the channel. If you have recommendations, if you want to see that, put it into the comments down below. But it turns out that if you do solve this, then the runtime here is going to be big O star, so we're eliminating the polynomial factors here, of approximately 1.84 to the n. Okay, so we had 2 to the n runtime before, now we have 1.84 to the n, which is actually a pretty dramatic drop. We would like to have this like down to like 1.0001 to the n or something, but this is significantly better than 2 to the n, way asymptotically smaller. Is this the best that we can do? No, and we're going to see another method to actually reduce this even further next. Okay, so let's actually get a faster method. And the idea behind an even faster method is to look a little further into this. So notice that we had one clause right here. It turns out that if we look 2 clauses in, we can actually get a better runtime just by analyzing things a little more. So in order to introduce this, we need to know what a pure literal is. So a pure literal in a formula is where it only appears in one form. So if we have something like x or something and some other clause where we had some stuff or x or something, so there in this whole formula, so there is no the negation of x, there's only the positive form of x, then that means in this entire formula, I might as well, without loss of generality, assume that we can just set x to be true throughout. So if there's no negation of x, just set x to be true the whole way through. It can only help you, it can't hurt you to set x to be true. Conversely, if there's only the negated version of x and no positive version, you might as well just set it to be false all the way through. And that makes things, obviously the formula gets a little simpler now, but it very well could be that there are no pure literals in the formula, which is totally possible. So let's deal with the situation that there are no pure literals in the entire formula. Okay, so let's analyze the condition that we had a little earlier. So we had something like x or y or z and some other formula, some other 3-sat formula. Well, if there's no pure literals in the entire thing, then if we look at x, we might as well, without loss of generality, assume that x negated is not in here, because if it's x or not x in here, then this clause is trivially satisfiable, and so we don't even need to consider that clause. We can make the formula even simpler. But let's just handle the generic case, where we have x here, x is not repeated in here, which means since there's no pure literal, there must be a negated version of x somewhere in here. Okay, so let's extract that one clause and then see what we can do with it. So what I'm going to do is I'm going to make this formula a little more simple by saying, let's say that there's a negated version of x in one of the other clauses, but the other two literals could be really anything. So these, again, could be positive or negated. Actually, I should use different variable names. So let's use A and B. And then and some other stuff. Okay, so we have one clause right here where we have an x. We have another clause where we have a negated version of x because we assume that there are no pure literals in the formula. So what can we do here? Well, let's focus on what we did earlier. So we had phi prime equaling that whole thing, and we analyzed the case of where phi prime subject to the case where x is true. Okay, so if x is true, this clause is obviously satisfied, but this one isn't yet. So then this clause right here is effectively reduced to A or B. Okay, because if x is true, this thing is false, so false or whatever is just the whatever. So this clause is reduced to A or B. So this one is going to be equal to, well, this thing is true, so we can just forget it. This second one is going to be A or B and then phi. Okay, so it's actually slightly smaller than the whole thing, because we eliminated this right here. And here we can actually, since we only have two literals right here, we can actually deal with them a lot easier. So let's try to make a faster algorithm out of this. So I'm going to call this 3-sat F for faster. And so I'm going to have the formula be called phi prime. So then we have the base cases as usual. So if phi prime is empty, we're going to return true. So that's not any different than before. So and then now let's deal with the case where there is a pure literal. So if phi prime has a pure literal, let's call it L. So if it has a pure literal L, we might as well just set that thing to be true all the way through. So I'm going to just return 3-sat F of phi prime subject to the case of L being true. Okay. So now let's try to extract those two clauses out. So we have x or y or z, and the negated version of x, or A or B, and that's going to be the formula phi prime. We might as well assume that it has two clauses at least, because if it has one clause, you can think about it as already satisfiable. So then now let's try to work with this then. So then if we will subject to the case where x is true, then if we look at this up here, then we might as well set like one of these two to be true, because in order for this clause to be satisfied, one of them has to be true anyway. So let's deal with that. So if we recursively call 3-sat faster on phi prime, where I'm going to set x to be true, and I'm also going to, in this case, set A to be true. You can, because it's symmetric, you can set B to be true. I'm just setting A because it's the first one. So if that's the case, I'm going to return true. Okay. Then let's think about what else could we do. So if this is not the case, then we can actually, here, if x is true and A is true, and let's say the formula is not satisfiable, then we don't know necessarily which of these is the culprit, right? So let's just try both. But we're going to do it in a smart way. We're going to have x to be true in the next one. We're going to set x to be true and A to be false and B to be true. Because that smaller clause has to have something to be true, and it has two things in it versus three. So what I'm going to do here is I'm going to call if 3-sat faster on phi prime, x is still true, A is going to be false this time, and then B is going to be true, then I'm going to return true. Okay. So then, well, now, if this is not satisfiable, then it must be that X is false. Because if X is true, we effectively enumerated all the possible options for A and B. They both can't be false because then that clause is not satisfied. If B is true, then it doesn't actually matter what A is because we tried true and false, and if neither of them is satisfied, then we're in trouble. So effectively, we've enumerated all the possible things we can do for X. So now let's do the recursive cases we did before, where we set X to be false. But then we have to deal with the clause that X is in right now, the XYZ clause. So let's deal with that clause. So if 3 sat f of phi prime, X to be true, false, X to be false. Need to keep thinking. So then Y we're going to set to true, and then we're going to return true in that case. And then as a final step, we're going to do the same case we did before. So if 3 sat f of phi prime, X to be false. In this case now Y has to be false. And then Z has to be true in order for the clause to be satisfied. And actually, since that's the only possible thing we can do, I'm just going to return that. Okay. So what is the runtime of this? Well, let's try to analyze the recursive cases. Let's do red. So T of n is going to be, let's see, well, this one right here has 2 variables that are fixed, and then this one has 2 variables that are fixed. So we're going to have 2 instances of T of n minus 2, and then here we have 2 instances of n minus 3. So we're going to have 2t of n minus 3 plus some polynomial runtime. And it's going to be swallowed up by the rest of this anyway, so it doesn't actually matter what it is as long as it's sufficiently small. So the advantage of this, you may think, okay, well, there are 2 things now versus 1. The advantage is that we have an n minus 2 now, not an n minus 1. So what is the actual runtime where we simplify all of this? Again, it's beyond the scope of this video, but if you solve this, it's going to be big O star of, it turns out to be 1.77 approximately to the n. And that's a little better. It's not significantly better like we had from 2 to the n down to 1.8 to the n, 8.4. And then now down to 1.77. It's slightly better, but it's definitely better. So you can actually go significantly better than this. So I'm not going to go over that in this video. This video is already long enough. But the basic idea is try to think about a satisfying assignment and how far it could possibly be from a different satisfying assignment. So if you have something maybe if you have an assignment where the formula is false, how far do you have to go in order to guarantee you can't possibly find another satisfying assignment? So that's something called local search. If you randomize the assignments, it turns out that you can get some bound in the runtime that's better than actually this. The state of the art is around 1.3 to the n, deterministic. It's about 1.3 to the n, and no one knows whether you can actually do better than that. And there are many, many different algorithms that have been proposed. It's a very complicated research area, but if you are interested in this, please leave comments down below. And if you want me to look at the more complicated examples, I'm happy to do so. So that was an intro into fast algorithms for NP-complete problems. Hopefully I can do some more in the channel in the future, but this is a quick and easy one, for the 3 sat problem.